All right, so now we're coming into part 3 of our notes on the derivative, all very important things that we want to be working on. And so the idea here is that what we want to work on is the numeric value of the derivative. This is just kind of a recap from what we've done before. This is called the modified form, just kind of reminding you that this one is when we want to actually just find one slope given a specific point that we're going to be interested in. So instead of using the general formula, which is f prime of x, which is the limit as h goes to 0 of f of x plus h minus f of x all over h, now what we want to do is know that this is going to be basically finding a specific value for the derivative of slope at a specific point x equal to c. Okay? So when we look at this, there's a couple of things just to kind of recap here. One, I'm going to let you do this problem basically on your own, which is I want to find the modified form of the definition of derivative. I just want to find f prime of 21. I don't want to find a general formula. I just want to go plug and chug right to what the slope is at 21. So we would do the limit as h goes to 0, and we would do f of 21 plus h minus f of 21 all over h, which in the next step, by simply plugging and chugging with our formula, would be the limit as h goes to 0 of the square root of 21 plus h minus 5 minus whatever f of 21 is. 21 minus 5 is 16, square root of 16 is 4, all over h. Now, the reason why I came back to this, and I know we did this in the previous set of notes, is where you're going to see the use of formulas like this, in addition to you just calculating them, is basically in the multiple choice section. And in the multiple choice section, what they're going to do is they're going to give you this limit, and then they're going to ask you, what is it? And you're going to have to recognize, first off, because this is the limit as h is going to 0, and you have this h over here, that this is a derivative, and that you have to be able to recognize what the function is and at what specific c value you're actually looking for. You're going to have to be able to recognize that this is the derivative of this function, the square root of x minus 5, at 21. So the key here is that you have to realize that these go together. This is your c plus h. And when you take that out, that's kind of like where the x was. So that can get you back to square root of x minus 5. This number that's here, once you decide what your f of x is and what your c value is of 21, then you should look at this and be able to say, well, is that f of 21? And you would plug that in and be like, okay, I am basically looking for the point 21 and f of 21, which is my 21 and 4. And so you want to be able to, if you see this, know what they're talking about. That's why we look at all of these different forms. We're eventually going to have shortcuts to this, where I actually don't have to calculate this limit using this long definition and doing all this algebraic work. So we'll have a shortcut, but what you're going to see is they're going to throw stuff like this at you in the multiple choice, and you're going to have to figure out what it's talking about. And you'll have to know that this is the derivative at 21 on that function. All right, let's go ahead and just finish this out while we're here. In this problem, we basically have the limit as h goes to 0 of the square root of 16 plus h minus 4 over h. What is our algebraic technique for multiplying with this or trying to figure out what this limit is? It's our rat-con technique. So I'm going to multiply by the conjugate. Square root of 16 plus h plus 4. Square root of 16 plus h plus 4. Okay, when we multiply by the conjugate, the top is going to end up being 16 plus h minus 16. And again, the bottom, don't multiply it out because that defeats the purpose of having it factored so that I can remove common factors. All right, which is going to give me the limit as h goes to 0 of basically h over h, square root of 16 plus h plus 4. Cancel the factor that's causing the problem. First we'll leave a 1. And at this point we can go ahead and not do as much writing. Go ahead and plug and chug. Put in your 0. Square root of 16 plus 0 is 4. 4 plus 4 is 8, so we get 1/8. So f prime of 21 is 1/8. And we have calculated our derivative at 21 using this modified form. Okay. Now, what I want to come down here, this alternate form is going to be very important for really what the point of our lesson is today, which is when is a function differentiable at x equal to c. And what we're going to do is, let me just kind of give you a picture that this definition of the derivative is exactly the same as what we did before. I'm just labeling things differently. So let's come in here and let's just draw a generic function that we're going to look at. So here's my function f of x. When I look at this function, and basically when we look at it, let's label some points on it. Now what we had done before is we had labeled the points c and f of c, which is going to be where we're interested in the derivative at. So here's c, here's my point, and I'm going to label this as c f of c, because if we're doing slopes, of course, we're going to have change in y over change in x. Now, what I did before is we did a distance of h away, and we created a point which was c plus h. And then I calculated its coordinates, and it was c plus h, f of c plus h. And that's how we came up with this definition up here, that we did the change in y over the change in x, and that's how we did our limit as h goes to 0. But what I want to do now is I'm going to kind of change my perspective. I'm going to leave this point as is. But instead of calling this point a distance of h away, I'm just going to call this x now. Some generic point x. And then I'm going to call, of course, this would be f of x. So the idea here is I'm just changing the label. That's it. I'm giving it the name x f of x to talk about a general point somewhere that's not the specific point that I'm talking about. Now, what we had done before is we would let the points get closer and closer together. So we would send this point along the curve heading towards it. And at that point, we were letting h go to 0. But if I'm calling this x now, and I'm letting the point get closer and closer and closer, where is x going as it gets closer and closer? It's going to c. So letting h go to 0 and letting x approach c are exactly the same thing, just labeling them differently. So this is really nothing more than change in y over change in x, slope of the secant line again, but we're just looking at it in a different perspective and letting the x approach c as opposed to letting h go to 0. And this is a classic way to help us with our differentiability, because now I have the option. Notice I put the point over on this side, but it could also end up over here and go this way. So we're going to let x approach c from both sides. And so that way we know that when is a function going to have a derivative, it would have a derivative only if this limit exists. All right, so we're just going to practice here for the first time just using this definition now that we have it. So we're going to find f prime of 21, which we already found above, by using this definition, just to kind of show you the differences. So we would do the limit as x approaches 21, because that's the c value I'm interested in. I'm going to do f of x minus f of 21 all over x minus 21. All right, so we're going to do the limit as x goes to 21 of the square root of x minus 5 minus f of 21, which was 4, all over x minus 21. Now, before I actually do the actual algebra to calculate this limit, if you take a look at this again, where are we going to see this? You're going to see this in the multiple choice section. What you're basically going to be, they're going to say, hey, what is this? This alternate form is actually a lot easier to determine what derivative you're taking, because right here is telling you what c is, where I'm interested in taking the derivative at, and then this first item right here is nothing more than my function. How do I know this is a derivative? Because x is approaching 21, I have a change in x, and then I have a function minus a value, which is probably the function value. So you should be able to look at this and immediately go, oh, hey, my function was square root of x minus 5, and I'm interested in the derivative at 21, that you should know what this is. Because they'll give you this, and then say pick from the following choices what it is, and you have to know it's f prime of 21. All right, so let's go ahead and do our RATCON again, except now My conjugate is square root of x minus 5 plus 4, square root of x minus 5 plus 4. Multiply out, I have the limit as x goes to 21 of x minus 5 minus 16. X minus 21 resists the multiplying on the bottom. Remember, you're just putting it out. It's already in factored form. You're like, oh, wait a minute. What's x minus 5 minus 16? That's x minus 21. Isn't that exactly the same factor as this? Again, let's save a little time. If we recognize it's the same factor, we can cancel it. We're left with that 1 on the top. And then I plug in my 21. Now this is x now, so x is going to 21. I'm basically taking the limit as x goes to 21 of 1 over square root of 21 minus 5. I have limit written there, so I can't put it in yet. Of x minus 5 plus 4, which by direct substitution is square root of 21 minus 5 plus 4, or square root of 16, 4 plus 4, 1/8, which is the same thing we found earlier. All right, so that kind of gives you the first little glimpse of using this. You know, it's pretty much about the same. If I was just calculating a specific derivative at a specific point, does it really matter if I use this form or whether I use that form? No. Feel free, pick whichever one you want. But what this one does is this is going to help me get to differentiability at a point. When does a derivative exist? So what we're basically asking here is, does f prime of c, does it exist? Okay? Now, if I go by this idea that if I'm using the alternate form, which is f prime of c is the limit as x approaches c, f of x minus f of c all over x minus c, that when will this limit exist? This limit exists exactly when the left limit and the right limit are the same. So that's essentially going to give us a way to determine whether or not a derivative exists at a point. Okay? Now, obviously, we're kind of thinking about what's going on here. We're saying that it's going to be differentiable, that first the graph is going to have to be continuous and connected. F of c is going to have to exist, and it must connect together in a way so that the slopes are going to kind of smoothly merge into each other, that there's going to be a limit process. All right, so let's kind of take a look at this and look at some examples. Here's our first example. I want to take a look at the differentiability of f of x equal to the absolute value of x minus 2 at x equal to 2. So I start with my alternate form of the definition. I'm basically trying to determine, does f prime of 2, does this exist or not? Okay, so I go, well, let's start calculating. The derivative at 2 is the limit as x approaches 2 of f of x minus f of 2 over x minus 2 using that alternate form. This will be the limit as x approaches 2 of absolute value of x minus 2 minus f of 2, 2 minus 2, 0, basically, over x minus 2. And then I'm going to pause here and go, wait a minute, that's piecewise. And whenever you have piecewise, remember you have to do the left and the right limits separately. So I'm going to break this apart now here, and I'm going to first do the right limit. I'm going to do the limit as x approaches 2 from the right. Now, what's the right piece of absolute value of x minus 2? That's x minus 2 over x minus 2, which of course is nice because that just cancels and leaves me with basically 1. And the limit of a constant is the constant. So the right limit is 1. You're like, okay, I'm on halfway there. Take a look at the left limit. Take the limit as x approaches 2 from the left. Now what's the left piece of absolute value? That's the opposite of x minus 2. This cancels, but now this limit is negative 1. What do we notice here? Our right limit is 1, our left limit is negative 1, so our conclusion is that the limit as x approaches 2 of f of x minus f of 2 over x minus 2 does not exist. And if that limit does not exist, that also means that our derivative doesn't exist. F prime of 2 does not exist. Okay, and then our third statement that we get out of this is that f of x is not differentiable at x equal to 2. Now, the other thing that I want to talk about here is kind of this connection between continuity and differentiability. You would be mistaken in this problem if you went, oh, is f of x continuous at x equal to 2? Because a lot of people get confused with continuity and differentiability and think we're talking about the same thing. The answer here is yes, this is continuous at x equal to 2. F of 2 exists because it's 0. The limit as x approaches 2 of f of x exists, and it happens to be 0. Think about what your graph looks like here. You basically have a absolute value graph that's moved to the right 2. So here's our nice little picture of this, and of course the limit of that exists, and it's 0. And notice that the limit as x approaches 2 of f of x equals f of 2. There's our three-part definition of continuity, so the answer to this is yes, the function was continuous at x equal to 2, but it's not differentiable. And the key here is what's causing it to not be differentiable. The fact is that the slope on the left of the point, the slopes are all -1. The slopes on the right of the point are all 1. So the idea is the left and the right, the slopes are approaching the same number from the left and the right. I can't draw a tangent line here. What is the feature of this that we're going to be looking for? This is what we call a cusp. Pretty much in general, if a function has a cusp, if f of x has a cusp at x equal to c, then your derivative at c does not exist. You're pretty much guaranteed, if there is a sharp corner or a cusp there, that the derivative limit definition that we're going to be using, this alternate form, your left limit and your right limit are going to be different. You're going to have a different slope on the left side of the cusp than you are on the right side of the cusp, and there's going to be a jump on the derivative, jumping from one slope value to another. And that's going to cause the derivative itself to have a discontinuity. So f prime of x is going to have a jump discontinuity at x equal to c. This is going to be bringing in toward our, when we start sketching our derivative. So right now, we basically have this idea of cusp are going to be the first kind of problem. All right, now let's take a look at example 9, another kind of classic problem to look at. So in this one, we're looking at the differentiability on a cube root function at x equal to 0. Now let's just do a little quick reminder of what a cube root looks like. It pretty much comes in, comes up, and then kind of goes this way. Our little Egyptian that we're looking at. And if I were to ask the question, which is a different question than differentiability, is f of x continuous at x equal to 0, and hopefully, and I'm not going to go through all the parts and write it down, but the answer is going to be yes. Does f of 0 exist? Yes, it's 0. What's the limit as x approaches 0 of f of x? It is 0. They are the same, so the answer is yes, it's continuous. But then let's talk about the differentiability here. All right, to determine differentiability, what we're basically saying is, does f prime of 0 exist? That's the question that I'm asking myself. So I go to that alternate form of the definition, and I'm going to take the limit as x approaches 0 of f of x minus f of 0 over x minus 0, using that alternate form. Plug in what we have. We're going to do the limit as x approaches 0. We're going to have the cube root of x minus 0 over basically x. Now, when we take a look at this, the idea is, all right, how do I do this derivative, or this limit? I'm doing the limit as x approaches 0 of the cube root of x over x. You think, what technique could I use here? You might want to go, well, wait a minute. this is a power of x, and that's a power. Can't I simplify this in some way? I'm going to rewrite this as the limit as x goes to 0 of x to the 1/3 over x to the first. And then remind myself that if I was simplifying algebraically, and my exponent rules would say that I should subtract my exponents. This is x to the 1/3, so 1/3 minus 1. So this is x to the negative 2/3. And then what does a negative exponent mean? That means, and this is all just algebra, 1 over x to the 2/3. And then I go, what's this limit? Can I calculate this limit? I couldn't calculate the limit back here because if I tried to plug in 0, I got that 0 over 0 indeterminate form, which means do more work, try to remove the discontinuity. So my more work was rewrite it in exponent form, use the exponent rules. That gets me to here. What happens now when I try to plug this in? This, when I try to do direct substitution, gives me 1 over 0. Is that still indeterminate? No. What this tells me is on the derivative, there must be a vertical asymptote, because this is either going to infinity or negative infinity. It actually goes to infinity on either side. If you look at the left, okay, and if we break this apart into the left, the limit as x goes to 0 from the left of 1 over x to the 2/3 is going to be infinity. The limit as x goes to 0 from the right of 1 over x to the 2/3 is negative infinity. Well, either way you go, this limit does not exist, which is pretty much telling us that, oh, okay, so the limit does not exist, which means that f prime of 0 does not exist, okay, which means that f of x is not differentiable at x equal to 0, because our limit did not exist when we did the definition of the derivative. And then the idea is, well, why did this happen here? Okay. Now in this one, if I start saying what's the graph of the derivative look like, f prime of x has a vertical asymptote at x equal to 0. How do I know that? Because I know the limit on the left and the limit on the right is going to infinity and negative infinity. There is this asymptotic behavior. But why did that happen? What in the world was going on here? Well, let's draw in our tangent line and take a look at this. So my tangent line, if I draw it in at x equal to 0, I get a vertical line. Now, why would a vertical line have a tangent, a slope that doesn't exist? Because the slope of a vertical line is undefined. Kind of our classic Algebra 1 definition here. And what's happening here is when we have this kind of coming in, this portion of the graph has what we call unusual steepness. And when a graph has unusual steepness, that's going to cause your tangent lines to become vertical, which means they have no slope. So it's continuous there, but it does not have a derivative because the tangent line, it has a tangent line. See up here, this one did not have a tangent line at all because I didn't know where to draw it. But this one has a tangent line to that point. However, the tangent line is vertical, which means its slope is undefined. So if a function, f of x, has, and I know this is not technical, but we're just going to go with it, has what we call unusual steepness at x equal to c, then the f prime of c does not exist. Now, I do want to caution you, though, that there are going to be functions. Don't think just because this has a point of inflection that every point of inflection is unusually steep. If I was doing the cubic, y equals x cubed, which is going to come in like this point right here actually does not have unusual steepness. It has unusual horizontalness. It's actually going to have a slope of 0 when it comes in here and then goes out this way. So it's kind of more along this line. You can also have functions where your slope doesn't have to be 0 or undefined. It could be along these lines, and if you draw the tangent line in, that tangent line actually does have a positive slope. So you just don't go by the fact that there's a point of inflection there. It actually doesn't even need to be a point of inflection at all. It just has to have unusual steepness there, okay? Where it comes in and it's very straight, regardless of what happens here and here, that if it's straight up and down there, that unusual steepness is going to cause you not to have a derivative. Right? I have one more example here we want to look at. Let's look at the differentiability of x to the 2/3. Maybe let's remind ourselves what this means in terms of a function. This is the cube root of x squared, just to kind of remind you. Is it continuous? Is f of x continuous at x equal to 0? Let's ask that question before I talk about the differentiability. See, in the first two examples, they were continuous, but they didn't have differentiability. So now, is f of x continuous here? Well, does f of 0 exist? Yes, 0. What's the limit as x approaches 0 of f of x? Well, what's happening on either side of this? Is this piecewise? Not really. Cube root of x squared. If you take a look at the graph is going to look something like this. It's going to come in and do something like that. So the limit exists. When you take a look at it on your calculator, this is going to be 0, and they're the same. So is it continuous? Yes. This is continuous at x equal to 0. But just as soon as I show you that graph, do you see a couple of things going on? This one I gave you mostly because of the example that not only does it have a cusp, it actually also has unusual steepness going into the cusp. So it's not a point of inflection, it's just a place where you're going to have both unusual steepness and a cusp. So now let's take a look. What happens on this? If I actually do the limit definition for f prime of 0, use the alternate form of f of x minus f of 0, x minus 0. This will be the limit as x goes to 0 of x to the 2/3 minus 0 over x. I'm going to do the same thing I did before in the previous one. I'm going to subtract. I'm going to do the limit as x goes to 0. This ends up being 1 over x to the 1/3. Okay? If I am taking a look at what's happening on the left and the right, the limit as x approaches 0 from the left of this 1 over x to the 1/3 is going to be negative infinity. The limit as x approaches 0 from the right of 1 over x to the 1/3 is going to be positive infinity. So we're still going to get the idea that there's going to be a vertical asymptote on the derivative, but again, this simply does not exist. So what's my conclusion about the differentiability? F prime of 0 does not exist. And we basically say f of x is not differentiable at x equal to 0. The derivative graph, f prime of x, has a vertical asymptote at x equal to 0 because I know the behavior before and after is going to negative infinity and infinity. But it's kind of like a jump, too, because it had a cusp, because it's negative infinity and infinity. And notice over here it was, oh, I had that wrong. That should have been infinity and infinity because I'm squaring it, which of course makes it positive. So this one was a just unusual steepness, and you still have a vertical asymptote. The derivative is just going to go to the same spot. Over here, you have vertical asymptotes that are going to different places. And you do kind of get this idea of a jump. All right? So let's come over here to a very important theorem, though. Now, in this, let's talk about continuity. I've shown you 3 examples where it was continuous, but not differentiable. But let's talk about if it was differentiable. If I take a look at the limit as x goes to c of f of x minus f of c all over x minus c. Clearly, if this exists, the first thing that we know in this is that f of c must exist. Because if it's differentiable, that says f prime of c exists. And so this is my definition for f prime of c. So the only way for that to exist is I have to be able to plug all that stuff in. The other thing that it tells me is that as you're approaching x equal to c, it must approach it in a smooth fashion so that the derivative is the same on, the slopes are the same on the left as they are on the right. And so it pretty much, it has to be continuous. If you are differentiable, then the function is continuous. And that is, think of this like your implication from your geometry class. And then we have the contrapositive, a little bit of geometry review here. The contrapositive says that if the function is not continuous at x equal to c, then it's not differentiable at x equal to c. Okay? And these mean exactly the same thing, because remember the implication is always exactly the same, equal to its contrapositive, the negation of switch and negate. Okay? So these mean exactly the same thing. So right there, we've learned another case of where you would have a function that's not differentiable. If it's not continuous, then it can't be differentiable. However, be very careful about stating that this is the same thing. If I say if f is continuous, is that enough for it to be differentiable, or do I have to check other things? I have to check other things. I just showed you 3 examples of issues that we might have. If f is continuous, then it may be differentiable. And there are 2 cases that we have to take out. So it will fail to be differentiable. I'll kind of bring down for this one. 1, fails to be differentiable if there is a cusp at x equal to c, and then the second time that it would fail to be differentiable if there is unusual steepness at x equal to c. And then the third case, kind of, if it's not continuous, would be if f is not continuous at x equal to c, then f is not differentiable at x equal to c. So that gives us our 3 things that we're going to look at. Now, I do want to caution you, though, that you have to be very, very careful about taking a look at a function that appears to be the same slopes on either side. Okay, so let's take a look at this piecewise function down here in example 12. I'm going to just draw a picture of it. We have our x squared, which is our nice parabola for x less than 1. So it'll come in here, come up, and we're going to include this point. So this is going to be 1, 1. And then I'm going to go ahead and do 2x plus 1. So at 1, I would have 3. And then from then on, we have a slope of 2, so up 2 over 1. And so the function is going to continue here, except for I need to have a hole on the end of this one. And so that's the picture of the graph. Now, the mistake that a lot of students are going to make is you kind of start looking at this and going, okay, if I've forgotten that if it's discontinuous, then it is not differentiable. I might come in here and say, well, the slopes of the tangent line coming across here, they are approaching, I'm having trouble sketching and actually hitting the curve here, that as x approaches c, the slope of the tangent line right at that point is about like that. And you go, wait a minute, that slope and the slope over here looks like they're exactly the same. So we're like, okay, let's take a look at this. If I were to take, and I'm not going to do the work for this, but let's say that I want to find the derivative for this piece. Your f prime of x is going to be 2x. And I'll let you do all the work for that elsewhere, or on your own. And the derivative of this piece of it is going to be simply 2. right? So I can kind of think about the derivative f prime of x as its own piecewise function, that the left piece is going to be 2x, and the right piece is going to be 2. And so the idea here is, because I'm now looking at this as a derivative function, and I want to say, well, what does that function actually look like? Well, let's kind of sketch it in. I'm going to add it right here onto my graph. Let me just get rid of this pink stuff. And add back in my function. Okay, so let's think about sketching this actual derivative in. So we have our derivative is 2x for the left piece. So, and I'll put this in green. So 2x goes through here, and at 1 it would be 2. And at this point I'm just going to put an open circle here. I'm just going to draw it everything except for x equal to 1. So that's that. And then we have at x equal to 2 over on this side, because it's constant. So here's our derivative. And then I'm like, well, what about that? Why can't I just fill that in and make that filled in right there? So right now, all I've done is this is x less than 1, this is x greater than 1. To figure out where the derivative exists, I really need to know, do I fill that in? Do I not fill that in? I'm not really sure what I should do there. What you have to remember is it doesn't really matter that this is connected here. What's going to matter if I'm actually trying to talk about the differentiability, even if the limit as x approaches 1 of whatever this derivative looks like is going to be 2. And the reason it's 2 is because the limit as x approaches 1 from the left of the derivative, all the tangent line slopes before 1 are approaching 2. All the tangent line slopes after 1 are approaching 2. So they're the same, so that limit exists. You will be tempted, totally tempted, to tell me that it's differentiable at x equal to 1. But you have to remember that differentiability has to come from the alternate form of the definition, not from looking at what the slopes of the tangent lines of all the points before and the tangent line slopes after. Even though they are having the same slope here and here, that does not make it differentiable. What we want to do is use this alternate form, and I think I left you, is that the same function? X squared and 2x, oh, it's 2x plus 1, okay. So let's go ahead and do the second part here and do the alternate form. So you really, if you wanted to see whether f prime of 1 exists, which is the question I'm asking, you do not look at the slopes before and after. What you have to do is go back to that definition and look at the limit as x approaches 1, f of x minus f of 1 all over x minus 1, which is going to be the limit as x approaches 1 of f of x minus, now what is f of 1? From our definition, f of 1 is 1 squared or 2. 1 squared or 1. So that's 1 all over x minus 1. Now here's where it gets interesting. This is piecewise. So I'm going to have to do this as a left limit and a right limit. So let's look at the limit as x approaches 1 from the left. What's the piece on the left piece of f of x? The left piece of f of x is x squared. So that's what we're going to use for f of x minus my f of 1, which was 1, over x minus 1. And we say, oh, wait a minute, that's a nice removable discontinuity. It's going to be x plus 1, x minus 1 over x minus 1. That goes away. Now I can substitute my 1 in and I get 2. There you go. I have a limit on the left of 2. Now I look at the limit on the right. So we're going to do the limit as x approaches 1 from the right. But now be very careful here. What's the right piece? The right piece on f of x is 2x plus 1. So I'm going to put in 2x plus 1 minus f of 1. Please do not plug 1 into this piece, because f of 1 is not going to change. F of 1 equals 1 for this entire problem. It's not defined on the 2x plus 1 piece. So you're still using the same point that's way up there at the top. And then I have over x minus 1, which if I simplify is the limit as x approaches 1 from the right of 2x over x minus 1. Oh, wait a minute. This is going to give me, when I plug it in, a number over 0, which tells me that the limit does not exist because there is some kind of a vertical asymptote going on. So even though this slope on the left and the right is the same, the limit doesn't exist for the derivative f prime of 1 does not exist because the limit definition doesn't exist. The left and the right aren't the same. So if I'm sketching the derivative, can I fill this in? The answer is no. It's actually got a hole at that location. I know that the limit is a hole because if I look at the slopes to the left and the slopes to the right, I'm headed to the same spot. The slopes are approaching the same value from the left and the right. However, the limit doesn't exist for the derivative at that point. Okay? All right, so I'm going to come over here. I'm going to leave example 13 for you to do on your own, and we'll come back and discuss that. And I'm going to stop this set of notes here.